On the morning of April 22, 1942, a 27-year-old naval aviator entered the Grumman Aircraft Engineering Corporation's manufacturing facility in Bethpage, New York. Lieutenant Commander Edward Henry O'Hare carried with him combat intelligence that would fundamentally alter American naval fighter aircraft design for the remainder of the Pacific War. O'Hare had recently received the Medal of Honor from President Franklin Roosevelt, awarded for his defense of the aircraft carrier USS Lexington against Japanese bomber formations on February 20, 1942. In that engagement, O'Hare had destroyed 5 enemy aircraft in less than 5 minutes using only 60 rounds of .50 caliber ammunition, a demonstration of aerial marksmanship that Navy tactical analysts would study for decades afterward. However, O'Hare's visit to Grumman's facility had nothing to do with publicity or recognition. The Bureau of Aeronautics had sent him to deliver first-hand combat data to the engineers designing America's next carrier-based fighter aircraft. The urgency behind this meeting stemmed from a harsh reality. American naval pilots were dying in aircraft that could not match Japanese fighter performance. The Grumman F6F Wildcat, the Navy's standard carrier fighter since 1940, had proven inadequate against the Mitsubishi A6M0, the primary fighter operated by Imperial Japanese Navy air groups throughout the Pacific theater. Performance data from fleet operations revealed the extent of the problem. The F4F4 Wildcat variant, which had entered service in early 1942, achieved a maximum speed of 318 miles per hour at optimal altitude. The Zero, by comparison, could reach 350 miles per hour. This 32-mile-per-hour differential meant that Zeros could choose when to engage and when to disengage from combat. American pilots flying Wildcats lacked this tactical flexibility. Climb rate presented an even more severe disadvantage. The Wildcat required approximately 4 minutes to reach 20,000 feet. The Zero could reach the same altitude in roughly half that time. In Pacific air combat, where altitude advantage often determined engagement outcomes, this disparity proved fatal. Japanese pilots could position themselves above American formations, attack from superior altitude, and break off engagement by climbing away faster than Wildcats could follow. Maneuverability differences were equally pronounced. The Zero could complete a 360-degree level turn in approximately 16 seconds at combat speeds. The Wildcat required approximately 30 seconds for the same maneuver. In close-range dogfighting scenarios, this meant that any American pilot who entered a turning engagement with a Zero was operating at a fundamental disadvantage that pilot skill alone could not overcome. Naval aviation doctrine, as taught at Naval Air Station Pensacola and reinforced in fleet training programs, explicitly instructed Wildcat pilots to avoid turning engagements. Standard tactical guidance emphasized boom and zoom attacks, dive from altitude, fire during a high-speed pass, and immediately climb back to safe altitude using speed and momentum. Wildcats were never to attempt sustained maneuvering combat with Zeros. The problem was that combat conditions rarely allowed perfect execution of doctrine. Zeros operated in formations designed to exploit the Wildcat's performance limitations. Japanese fighter tactics, refined through 2 years of combat experience in China and the early Pacific campaigns, specifically targeted the weaknesses in American hit-and-run approaches. Zero pilots would position 1 or 2 aircraft as bait, drawing American fighters into attacks, while other Zeros waited at altitude to intercept during the climb-out phase when Wildcats were most vulnerable. Between December 7, 1941 and April 1942, the Navy had lost 42 Wildcats in combat operations. After-action reports from surviving pilots consistently described situations where adherence to doctrine had failed to provide adequate protection. The aircraft simply lacked sufficient performance margin to reliably execute the tactics that doctrine required. If you're interested in evidence-based World War II aviation history that examines how combat feedback shaped aircraft development, Please like this video and subscribe to the channel. Leave a comment telling us where you're watching from. Edward Henry O'Hare had entered naval aviation through the Naval Academy at Annapolis. Graduating in 1937, he completed flight training at Naval Air Station Pensacola in 1940 and received his designation as a naval aviator that same year. By early 1942, he was assigned to Fighting Squadron 3, based aboard the carrier USS Lexington, operating in the Pacific Theater as part of the fleet response to Japanese expansion following Pearl Harbor. O'Hare's combat experience with the Wildcat provided him with detailed understanding of the aircraft's capabilities and limitations under actual engagement conditions. Between January and April 1942, he flew 14 combat missions in the F4F3 variant. These missions included combat air patrol duties, bomber escort assignments, and interception operations against Japanese reconnaissance and strike aircraft. The engagement that resulted in O'Hare's Medal of Honor demonstrated both the potential effectiveness of the Wildcat's armament and the tactical vulnerabilities created by its performance limitations. On February 20, 1942, Lexington's radar detected incoming Japanese bombers approximately 70 miles from the carrier. O'Hare and his wingman Lieutenant Junior Grade Marion DeFilho were vectored to intercept 9 Mitsubishi G-4M Betty bombers approaching the task force. During the interception, DeFilho's guns jammed, leaving O'Hare as the sole defender against the entire bomber formation. O'Hare attacked repeatedly, destroying 5 bombers through precise gunnery and tactical positioning. His ammunition expenditure, 60 rounds total to destroy 5 aircraft, represented extraordinary accuracy by any measure. Navy analysis of the engagement determined that O'Hare had achieved an average of 12 rounds per kill, far below typical expenditure rates. However, O'Hare's after-action report also documented the limitations he encountered. The Wildcat's rate of climb had forced him to begin his interception from a lower altitude than optimal tactical doctrine recommended. He had been unable to position himself for ideal deflection shots on the first pass because the aircraft could not gain altitude quickly enough. The engagement had required multiple attack runs, partly because the Wildcat lacked the performance to reposition efficiently between passes. Other pilots in Fighting Squadron 3 reported similar experiences. Lieutenant James Gray, an experienced aviator with 30 combat missions, was killed on February 21, 1942, during an engagement with Zeros near Rabaul. Gray's wingmen reported that Gray had followed standard doctrine precisely, diving from altitude, engaging the target, and attempting to climb back out. The Wildcat's climb rate had been insufficient to regain safe altitude before a Zero repositioned and attacked from above. The official investigation into Gray's death cited pilot error, suggesting that Gray should have maintained higher speed during the climb-out phase. However, pilots who reviewed the findings noted that Gray had been executing the maneuver correctly according to training standards. The issue was not pilot technique but aircraft performance. The Wildcat simply could not climb fast enough to execute the doctrine reliably against an opponent with the Zero's capabilities. By April 1942, O'Hare had observed 17 pilots from various squadrons killed in Wildcat versus Zero engagements. Many of these losses occurred in situations where pilots were following approved tactical procedures. The common factor was insufficient performance margin. Wildcats could not climb fast enough, accelerate quickly enough, or disengage reliably enough to execute the boom and zoom tactics that doctrine required. O'Hare discussed these observations with his commanding officer, Lieutenant Commander John Thatch. Thatch had developed a defensive tactic called the Thatch Weave, which used mutual support between paired Wildcats to compensate for individual aircraft performance deficiencies. The weave helped Wildcat pilots survive, but it was fundamentally a defensive measure, not an offensive solution. Victory in the Pacific Air War required aircraft that could match or exceed Japanese fighter performance. not just defensive tactics to minimize losses. The Grumman Aircraft Engineering Corporation had begun preliminary design work on a Wildcat replacement in early 1941, months before the United States entered the war. William Schwendler, Grumman's chief design engineer, led the development team. Schwendler had joined Grumman in 1930 after working for the Curtiss Aeroplane and Motor Company. He had previously designed the F-3F biplane fighter and had served as lead engineer on the F-4F Wildcat program. His experience with naval aviation requirements and carrier operations made him the logical choice to head the new fighter project. Initial design specifications for the XF6F called for a single-seat fighter powered by a Wright R2600 Cyclone engine producing approximately 1,700 horsepower. The proposed aircraft would mount 6 .50 caliber M2 Browning machine guns and include armor protection for the pilot and self-sealing fuel tanks. Estimated performance included a top speed of approximately 375 miles per hour and a service ceiling above 35,000 feet. Grumman constructed the first prototype, designated XF6F1, in early 1942. The aircraft incorporated several improvements over the Wildcat, including wider set landing gear for improved carrier deck handling, hydraulically operated landing gear to replace the Wildcat's manual crank system, and improved cockpit visibility through repositioning of the canopy structure. However, the R2600 engine installation presented cooling problems during initial testing, and performance projections indicated the aircraft would not provide sufficient advantage over the Zero to justify production. The Bureau of Aeronautics recognized that combat data from operational squadrons needed to inform final design decisions. Engineering projections and theoretical performance calculations could not replace information from pilots who had actually fought against Japanese aircraft. The Bureau decided to send a combat-experienced aviator to Grumman to provide direct feedback to the design team. O'Hare was selected for this assignment because he combined several critical qualifications. First, he had extensive recent combat experience against Zero's 14 missions over 4 months, including multiple engagements where he had survived situations that killed other pilots. Second, his Medal of Honor recognition provided credibility that would ensure engineers and Bureau officials took his recommendations seriously. Third, his demonstrated skill as an aviator meant his observations reflected actual aircraft capabilities, rather than pilot limitations. The Bureau of Aeronautics issued orders sending O'Hare to Bethpage immediately following the Medal of Honor ceremony on April 21, 1942. His instructions were explicit. Provide Grumman's engineering team with complete information about Zero performance characteristics, Wildcat deficiencies, and the specific improvements American pilots needed to achieve parity or superiority in Pacific air combat. O'Hare arrived at Grumman's Bethpage facility on the morning of April 22, 1942. Meeting included William Schwendler and approximately 8 other engineers from Grumman's design department, along with 2 representatives from the Bureau of Aeronautics who attended to document the discussion for official records. The conference lasted approximately 4 hours. Schwendler took extensive notes. Navy records indicate 18 pages of handwritten technical observations and design recommendations. The discussion covered 4 main areas: Zero performance characteristics, Wildcat operational deficiencies, successful Wildcat features worth retaining, and specific improvements required in the next generation fighter. O'Hare began by describing Zero capabilities in detail. He provided specific performance data based on combat observations: top speed exceeding 350 miles per hour, climb rate to 20,000 feet in approximately 2 minutes exceptional, maneuverability at all speeds and operational range exceeding 1,500 miles with external fuel tanks. He explained how Zero pilots exploited these advantages tactically, using altitude superiority to control engagement timing, superior climb rate to escape unfavorable situations, and maneuverability to defeat American boom and zoom attacks. Japanese tactical doctrine, as O'Hare observed it, emphasized patience and position. Zero pilots rarely committed to attacks unless they held altitude advantage. They would climb above American formations, wait for American fighters to commit to bomber escort or ground attack missions, then attack during vulnerable moments when Wildcats were climbing, turning, or otherwise operating at reduced energy states. The Zero's performance envelope allowed this patient approach. They could wait for optimal conditions because they could outclimb and outmaneuver opponents if situations developed unfavorably. Regarding Wildcat deficiencies, O'Hare provided detailed feedback covering multiple systems. The Wright R1820 Cyclone engine S 1,200 horsepower output was insufficient for the aircraft's weight and mission requirements. Pilots needed more power for faster acceleration, higher top speed, and improved climb rate. Every combat situation O'Hare described involved circumstances where additional engine power would have provided tactical options that didn't exist with current capabilities. The manual landing gear system presented operational hazards. Wildcat pilots had to crank a hand-operated mechanism 29 times to extend the landing gear fully. During carrier approaches, this meant flying with one hand while cranking with the other, reducing control precision during a critical phase of flight. Several accidents had occurred when pilots became distracted by the gear cranking process during approach and landing. Cockpit visibility was inadequate for combat operations. The Wildcat's canopy design and fuselage structure created blind spots that prevented pilots from maintaining visual contact with threats approaching from certain angles. In air combat, where situation awareness often determines survival, these blind spots were potentially fatal. However, O'Hare also emphasized features that made the Wildcat effective when it could bring its weapons to bear. The aircraft's 6.50 caliber Browning M2 machine guns provided devastating firepower. Each gun fired approximately 800 rounds per minute, and the combined battery could destroy most Japanese aircraft with a short burst. The ammunition capacity, approximately 240 rounds per gun in the F4F4 variant, gave pilots sufficient combat endurance for multiple engagements. The Wildcat's structural durability exceeded that of Japanese fighters. Armor protection around the cockpit and engine, combined with self-sealing fuel tanks, meant American pilots could survive damage that would destroy a Zero. O'Hare noted multiple instances where Wildcats returned to carriers with significant battle damage. Japanese fighters, built for maximum performance with minimal weight, lacked equivalent protective features. Schwendler asked specific technical questions throughout the discussion. What altitude ranges saw most combat? Between 10,000 and 20,000 feet. What speeds were typical during engagements? Between 250 and 350 miles per hour. How did Zero performance vary with altitude? Minimal degradation up to 20,000 feet. More pronounced above 25,000 feet. What was the typical duration of combat engagements? 5 to 15 minutes, though some extended longer. Based on this discussion, Schwendler and O'Hare identified 3 critical requirements for the new fighter: substantially increased engine power to achieve performance superiority over the Zero, improved cockpit visibility to enhance situational awareness, and hydraulically operated landing gear to improve carrier operation safety. Secondary improvements included additional armor protection and provisions for increased ammunition capacity. The most significant decision emerging from the meeting concerned engine selection. The Pratt & Whitney R2800 double Wasp radial engine, which produced 2,000 horsepower, was available and already in production for the Vought F4U Corsair. Installing this engine in the F6F design would require substantial airframe modifications, larger engine mount, reinforced structure to handle increased torque, modified cowling for cooling, but would provide the power increase necessary to exceed Zero performance. 4 days after O'Hare's visit to Bethpage, On April 26, 1942, the Bureau of Aeronautics issued a formal directive to Grumman modifying the F6F development contract. The directive ordered specific design changes to the second XF6F prototype, designated XF6F3, incorporating recommendations from the April 22 conference. Primary among these changes was engine replacement. Grumman was directed to install the Pratt & Whitney R2800010 double WASP engine in place of the originally specified Wright R2600. This change increased available power from 1,700 to 2,000 horsepower, a 17% improvement that would translate directly into enhanced speed, climb rate, and acceleration. The directive also mandated cockpit repositioning. The fuselage structure would be modified to mount the cockpit approximately 3 inches higher than the original XF6F1 design, improving the pilot's sightlines and reducing blind spots. This change required redesigning the forward fuselage structure and modifying the canopy framing. But Navy analysis determined the visibility improvement justified the additional engineering work. Hydraulically operated landing gear replaced the manual system used in the Wildcat. This change required installing hydraulic pumps, lines, and control mechanisms, adding weight and complexity, but eliminating the operational hazards associated with hand-cranked gear extension during carrier approaches. Additional armor protection was specified for areas around the pilot, oil tank, and fuel system. The Bureau directed Grumman to install the maximum armor weight the airframe structure could support, while maintaining acceptable performance characteristics. This resulted in adding 212 pounds of protective armor plate to the design, concentrated in areas most vulnerable to enemy fire based on combat damage analysis from Wildcat operations. The armament configuration remained 6 .50 caliber machine guns, matching the Wildcat's weapon fit. However, the Bureau directed that wing structure be designed to accommodate future upgrades to 8 guns or 20 mm cannon installations, if field testing indicated additional firepower was necessary. These modifications represented substantial changes to the basic F6F design. Schwendler's engineering team effectively redesigned major portions of the aircraft in 8 weeks, an extraordinarily compressed timeframe, reflecting the urgency Navy leadership attached to fielding an improved fighter. Normal aircraft development programs allocated months or years for such modifications. The F6F program had weeks. The redesign work occurred simultaneously with ongoing production preparations at Grumman's Bethpage facility. Plant Number 3, a new manufacturing building constructed specifically for F6F production, was still under completion while engineers finalized the modified design. This parallel approach carried substantial risk if the design changes proved unsatisfactory during testing. Production facilities would require reconfiguration, causing delays the Navy could not afford. On July 30, 1942, test pilot Robert Hall conducted the first flight of the modified XF6-3 prototype at Grumman's Bethpage facility. The aircraft represented the culmination of 14 weeks of intensive engineering work implementing the design changes ordered in April. The XF6F3 showed substantial performance improvements over both the Wildcat and the original XF6F1 prototype. Initial flight testing measured a maximum speed of 376 miles per hour at 17,300 feet, 58 miles per hour, faster than the F4F4 Wildcat and 26 miles per hour faster than Japanese intelligence estimates for the 0's top speed. Climb rate testing measured 3,240 feet per minute, approximately 40% faster than the Wildcat's climb performance. Hall's initial evaluation noted several positive characteristics. Control response was excellent throughout the speed range. The aircraft handled smoothly during landing approaches. Visibility from the redesigned cockpit was substantially better than the Wildcat. The hydraulic landing gear operated reliably and quickly. Overall handling qualities suggested the aircraft would be straightforward for fleet pilots to transition into from the Wildcat. However, the initial flight testing also identified issues requiring correction. Engine cooling proved inadequate at high power settings. Cylinder head temperatures exceeded acceptable limits during sustained climbs. Landing gear extension time, while faster than the Wildcat's manual system, still took longer than optimal for carrier operations. Gun harmonization required adjustment to ensure all 6 weapons converged properly at combat ranges. Schwendler's team implemented solutions over the following 3 weeks. Cooling problems were addressed by modifying the engine cowling design to increase airflow across the cylinder heads. Landing gear extension speed was improved by increasing hydraulic system pressure. Gun harmonization was corrected by adjusting mounting fixtures. By late August 1942, the XF-63 prototype had completed sufficient testing to validate the basic design. The Bureau of Aeronautics authorized transition to production on October 3, 1942, when the first production F6F completed its initial flight. This represented extraordinarily rapid progression from prototype to production, less than 10 weeks from first flight to production authorization. Normal Navy procurement processes typically required 6 to 12 months for this transition. The compressed timeline reflected the operational urgency driving the program. Production planning called for aggressive manufacturing ramp-up. Grumman projected delivering 12 aircraft by the end of 1,942, in the first quarter of 1943, and approximately 500 per month by mid-1943. These projections required hiring additional workers, installing new manufacturing equipment, and implementing 24-hour production schedules. Bethpage's manufacturing facilities would operate continuously 3 8-hour shifts, 7 days per week. The production plan also incorporated provisions for rapid design improvements based on fleet feedback. Unlike traditional procurement programs where design was frozen at production authorization, the F6F program included procedures for implementing modifications to aircraft already in production. This allowed for continuous improvement as operational experience identified refinement opportunities. Fighting Squadron 9, designated VF9, became the first Navy unit to receive production F6F Hellcats in January 1943. The squadron was based at Naval Air Station Norfolk, Virginia, under command of Lieutenant Commander Philip Torrey, an experienced naval aviator with 9 years of service and combat experience flying Wildcats in the Pacific. The transition from Wildcat to Hellcat required comprehensive pilot familiarization with the new aircraft's capabilities and characteristics. While both aircraft were single-engine, single-seat fighters manufactured by Grumman, the performance differences were substantial enough to require adjusted tactical approaches and modified operational procedures. Physical dimensions illustrated the scale difference between the two aircraft. The Hellcat measured 33 feet 7 inches in length, compared to the Wildcat's 28 feet 10 inches. Wingspan increased from 38 feet to 42 feet 10 inches. Empty weight rose from 5,758 pounds to 9,238 pounds, a 60% increase reflecting the larger engine, additional structure, increased armor, and enhanced systems. Performance improvements exceeded the weight increase penalties. The Hellcat's 2,000 horsepower R2800 engine delivered maximum speed of 380 miles per hour at 17,300 feet, 62 miles per hour faster than the Wildcat. Climb rate reached 3,500 feet per minute, 52% faster than the Wildcat's 2,300 feet per minute. Combat radius with a 150-gallon drop tank was 1,040 miles, compared to 950 miles for a similarly equipped Wildcat. V-Finane's training program covered 5 main areas: basic aircraft familiarization, advanced maneuvering, gunnery qualification, formation tactics, and carrier operations. Pilots required approximately 15 flight hours to achieve basic proficiency in the Hellcat, followed by 25 to 30 hours of advanced training to prepare for combat operations. Basic familiarization emphasized the differences pilots would encounter. The Hellcat's control forces were heavier than the Wildcats, requiring stronger input for rapid maneuvering. The increased weight meant higher landing speeds, approximately 76 miles per hour compared to 68 for the Wildcat. The wider landing gear track improved stability during carrier landings, but pilots needed to adjust their approach techniques to account for the aircraft's higher mass and different handling characteristics. Advanced maneuvering training focused on exploiting the Hellcat's performance advantages. Pilots learned to use the superior climb rate to maintain altitude advantage over potential opponents. They practiced high-speed dives and pull-outs, developing confidence in the airframe's structural strength. They trained in rapid acceleration from cruise speeds to maximum velocity, recognizing this capability as crucial for executing boom and zoom attacks. Gunnery training emphasized accuracy with the 6.50 caliber machine guns. Each gun was loaded with approximately 400 rounds, providing roughly 40 seconds of firing time if all guns were fired continuously. Doctrine called for short, controlled bursts of 1 to 2 seconds, allowing pilots to engage multiple targets without exhausting ammunition. VF-9's gunnery training stressed deflection shooting and range estimation skills essential for successful aerial combat. Formation tactics incorporated lessons learned from Wildcat combat operations. The standard 4-plane division remained the basic tactical unit, but formations were spaced wider to prevent mutual interference during high-speed maneuvering. Communication procedures emphasized brevity and clarity, as radio chatter during combat could obscure critical tactical information. Carrier qualification required each pilot to complete a minimum of 6 successful arrested landings aboard a training carrier before assignment to an operational carrier. The Hellcat's higher approach speed and greater mass required precise technique during the landing pattern. Pilots needed to maintain proper lineup and glide path while managing power settings to ensure they caught the arresting wire without excessive impact. By August 1943, VF-9 had completed training and was declared ready for combat deployment. The squadron embarked aboard USS Essex, CV-9, as part of Carrier Air Group 9. Essex was the lead ship of a new class of fleet carriers displacing 27,100 tons and capable of operating air groups of approximately 90 aircraft. The carrier deployed to the Pacific as part of Task Force 15, which also included USS Yorktown, CV-10, and USS Independence, CVL-22. Task Force 15's assignment was to conduct strikes against Japanese-held islands in the Central Pacific, demonstrating American naval air power's growing capability and testing the Hellcat's combat effectiveness. The first target was Marcus Island, a small atoll located approximately 850 nautical miles northwest of Wake Island. Japanese forces had occupied Marcus since the 1920s and had developed it into a forward staging base with airfield facilities, radar installations, and supply depots. Intelligence estimates indicated Marcus was defended by approximately 35 Japanese aircraft, primarily Zeros, along with heavy anti-aircraft artillery. The island's garrison totaled roughly 2,500 personnel, including aviation ground crews, defense forces, and support units. American planners assessed that a surprise dawn attack could destroy significant Japanese assets before effective defense could be organized. Task Force 15 approached Marcus during the night of August 30th to 31st, 1943, positioning approximately 150 miles southeast of the target. Strike planning called for launching the first wave at 4:15 a.m., time to arrive over Marcus at sunrise when visibility would favor attacking the aircraft, but Japanese fighters would have difficulty launching intercepts. VF-9, led by Lieutenant Commander Torrey, launched 16 Hellcats as part of the initial strike wave. Their mission was to suppress Japanese air defenses by destroying aircraft on the ground and providing fighter cover for the bomber and torpedo aircraft attacking port facilities and supply depots. The Hellcats formed up in the darkness using running lights, then proceeded to Marcus at low altitude to avoid radar detection. The strike force arrived over Marcus at 5:50 a.m. as planned. Japanese forces appeared unprepared, no fighters were airborne, and anti-aircraft fire did not commence immediately. Tori's division initiated the attack, diving on the airfield from 8,000 feet. They strafed parked aircraft with .50 caliber fire, destroying 6 aircraft on the ground during the first pass. Subsequent divisions followed at 30-second intervals, maintaining continuous pressure on Japanese positions. The concentrated firepower from 16 Hellcats destroyed an estimated 23 aircraft on the ground, damaged fuel storage facilities, and suppressed anti-aircraft positions sufficiently to allow bombers to attack without prohibitive losses. Japanese defenders eventually organized effective response. Anti-aircraft batteries engaged American aircraft, and 2 Hellcats were shot down during low-altitude strafing runs. One pilot, Ensign Richard Foster, was killed when his aircraft was hit by 40 mm fire during a second pass over the airfield. The other pilot, Lieutenant Junior Grade Walter Haas, successfully parachuted and was recovered by submarine USS Skate 3 days later. No Japanese fighters managed to launch during the attack. The surprise had been complete, and American suppression of the airfield prevented Japanese aircraft from taking off. This represented optimal conditions for the Hellcat's combat. Debut: the aircraft demonstrated its effectiveness in ground attack missions without facing air-to-air opposition. However, pilot assessments from the Marcus Island strike provided valuable initial combat feedback. The Hellcat's high speed and structural strength made it effective for diving attacks. The 6 .50 caliber machine guns delivered devastating firepower against ground targets. Visibility from the redesigned cockpit allowed pilots to maintain better situational awareness during the chaotic conditions of a multi-aircraft strike. The hydraulic landing gear operated reliably during carrier recovery operations following the mission. The Hellcat's first air-to-air victory occurred on September 1, 1943, when Hellcats from USS Independence intercepted a Japanese Kowanishi HK Emily flying boat conducting reconnaissance near Howland and Baker Islands in the Central Pacific. The engagement provided the first combat test of the Hellcat in its primary designed role, destroying enemy aircraft in air-to-air combat. Lieutenant Junior Grade Richard Loesch and Ensign Arthur Nyquist were flying combat air patrol approximately 40 miles north of their carrier when Independence's fighter director radar detected an unidentified contact at 4,000 feet altitude, range 35 miles. The fighter director vectored Loesch and Nyquist to intercept, providing continuous position updates as they closed with the target. The target was identified as an H-8 flying boat, a 4-engine maritime patrol aircraft with defensive armament including 5 20mm cannons and multiple machine guns. Japanese H-8K aircraft were used for long-range reconnaissance and occasionally for bombing missions against isolated island garrisons. They were relatively slow, maximum speed approximately 290 miles per hour, but heavily defended and difficult to shoot down without multiple attack passes. Loesch and Nyquist approached from above and behind, positioning for a stern attack that would minimize exposure to defensive fire. Loesch initiated the engagement, diving from 6,000 feet and opening fire at approximately 400 yards range. His .50 caliber fire struck the H-8K's port wing and fuselage, causing visible damage but not destroying the aircraft. The flying boat's defensive gunners returned fire, forcing Loesch to break off after his initial pass. Nyquist attacked from a different angle, approaching from the H-8K's port side to divide the defensive gunner's attention. His burst hit the cockpit area and port engines, causing the flying boat to lose altitude and trail smoke. The aircraft descended in a shallow glide toward the water while continuing to return defensive fire. Loesch repositioned for a second attack, this time approaching from the starboard side. His second burst ignited fuel in the H-8K's starboard wing tanks. The flying boat's wing separated approximately 15 seconds later, and the aircraft crashed into the ocean. No survivors were observed. The entire engagement lasted approximately 3 minutes from initial contact to crash. This first aerial victory demonstrated several Hellcat capabilities. The aircraft's speed advantage, approximately 90 miles per hour over the H-8K, allowed the fighters to control engagement geometry, approaching from optimal angles, and repositioning between attacks without being trapped in prolonged exposure to defensive fire. The .50 caliber armament proved adequate for destroying a large, heavily constructed aircraft, though multiple passes were required. The Hellcat's structural strength allowed it to maneuver aggressively during attacks without concern about airframe overstress. However, this engagement against a slow, non-maneuvering target did not test the Hellcat's performance against Japanese fighters. That test came in October 1943 during strikes against Wake Island. On October 5, 1943, Task Force 14, comprising 6 fleet carriers with approximately 200 Hellcats, conducted strikes against Japanese installations on Wake Island. Wake had been captured by Japanese forces in December 1941 and had been developed into a significant forward base with airfield facilities, garrison troops, and coastal defense batteries. American intelligence estimated the base was defended by approximately 35 to 40 Japanese fighters, primarily as 6 M0s. The strike was planned as a large-scale attack designed to destroy Japanese air assets and demonstrate American naval aviation's growing strength in the Central Pacific. Unlike the Marcus Island strike, where surprise prevented Japanese fighter response, the Wake Island operation anticipated significant air-to-air combat. This would provide the first major test of Hellcat performance against Zero fighters under conditions approximating sustained combat operations. American forces launched the first strike wave at dawn, comprising 48 Hellcats as fighter escort, 36 SBD Dauntless dive bombers, and 24 TBF Avenger torpedo bombers. The Hellcats were divided into 2 groups, 32 providing close escort for the bombers, and 16 conducting fighter sweep ahead of the main strike to suppress Japanese air defenses. Japanese radar detected the incoming strike approximately 60 miles from Wake. Defenders scrambled all available fighters, approximately 34 Zeros based on post-battle analysis. The Japanese force climbed to intercept altitude and positioned to attack the bomber formation, following standard doctrine of prioritizing bombers over escort fighters. The fighter sweep Hellcats encountered the climbing Zeros at approximately 12,000 feet, 15 miles northeast of Wake. The engagement began with the American fighters diving through the Japanese formation, executing boom and zoom attacks that exploited the Hellcat's speed and dive performance advantages. Several Zeros were damaged or destroyed during these initial passes, but the Japanese formation maintained cohesion and continued toward the bomber stream. Close escort Hellcats engaged as Zeros attempted to attack the bombers. The resulting combat involved approximately 66 aircraft, 32 Hellcats and 34 Zeros operating in a congested airspace volume approximately 5 miles in diameter. Engagements occurred simultaneously at multiple altitudes between 8,000 and 15,000 feet as individual aircraft maneuvered for position. Combat conditions tested the specific capabilities. O'Hare had emphasized during his April 1942 meeting with Grumman engineers. Hellcat pilots could execute boom and zoom attacks effectively because their aircraft could dive rapidly, fire during high-speed passes, and climb back to altitude faster than Zeros could follow. When Zeros attempted to force turning engagements, Hellcats could refuse the fight by accelerating away or climbing out of range. The performance advantage had reversed. Now American fighters controlled engagement timing. Japanese pilots attempted tactics that had succeeded against Wildcats: positioning at altitude, waiting for vulnerable moments, attacking during climbs or turns. However, these tactics were less effective against Hellcats. American fighters could climb to or above zero altitude more quickly, reducing the altitude advantage Japanese pilots relied on. Hellcats could also maintain higher speeds during combat maneuvering, making them difficult for Zeros to trap in disadvantageous positions. The engagement lasted approximately 28 minutes. American pilots claimed 31 Zero kills, though post-war analysis indicates the actual number was likely 22 destroyed plus several damaged. 4 Hellcats were lost, 2 to Zero fighters and 2 to anti-aircraft fire. The remaining Hellcats returned to their carriers with varying degrees of battle damage, demonstrating the aircraft's structural resilience. The kill ratio, approximately 5.5 to 1 in favor of American forces, represented substantial improvement over typical Wildcat combat outcomes. More significantly, bomber losses were minimal despite the large Japanese fighter presence. Only 1 SBD and 1 TBF were shot down during the entire operation. The Hellcat escort had successfully protected the strike aircraft while also destroying a significant portion of Wake's fighter defense. Post-mission debriefings provided detailed feedback about Hellcat combat characteristics. Pilots reported that the aircraft's speed and climb rate advantages were decisive. They could engage when tactical conditions favored them and disengage when conditions did not. This control over engagement parameters represented fundamental tactical superiority that pilot skill alone could not overcome. A mediocre pilot in a Hellcat had better survival prospects than an excellent pilot in a Zero, simply because the aircraft's performance provided more options for surviving mistakes. The most significant demonstration of Hellcat superiority over Japanese fighters occurred on December 4, 1943, during strikes against Kwajalein Atoll in the Marshall Islands. This engagement involved the largest concentration of Hellcats deployed to that date, 91 aircraft from 3 carriers against approximately 50 Japanese fighters defending the atoll. Kwajalein was a major Japanese base in the Marshall Islands chain, with extensive airfield facilities, port installations, and garrison forces. American intelligence estimated the base maintained 50 to 60 operational aircraft, including both fighters and attack aircraft. The base supported Japanese operations throughout the Central Pacific and represented a significant target for American offensive operations. Task Force 50, comprising USS Lexington, CV-16, USS Yorktown, CV-10, and USS Cowpens, CVL-25. The American strike force launched at 5:30 a.m. On December 4th, 91 Hellcats provided fighter escort and sweep, supported by 42 SBD dive bombers and 36 TBF torpedo bombers. The entire formation, 169 aircraft, proceeded to Kwajalein in coordinated waves, with fighters arriving first to suppress air defenses. Japanese defenders detected the incoming strike and scrambled all available fighters, approximately 50 Zeros based on post-battle analysis. The Japanese force climbed to intercept altitude and positioned to attack the bomber formations, following standard doctrine emphasizing bomber destruction as the primary objective. The engagement that followed represented the largest air battle in the Central Pacific to that date. Combat began when American fighter sweep elements engaged climbing Zeros approximately 20 miles northeast of Kwajalein. Within minutes, the entire airspace above the atoll became a massive dogfight involving approximately 140 aircraft, 91 Hellcats and 50 Zeros. The battle demonstrated conclusively that the Hellcats' performance advantages translated into tactical superiority under large-scale combat conditions. Zero pilots attempted aggressive tactics that had worked effectively against Wildcats: diving attacks from altitude, attempts to force American fighters into turning engagements, and coordinated attacks by multiple aircraft against single targets. However, these tactics were substantially less effective against Hellcats. American pilots exploited their aircraft's capabilities systematically. When Zeros attacked from above, Hellcats could accelerate away before Japanese fighters could achieve firing position. When Zeros attempted to force turning fights, Hellcats could disengage by climbing away faster than Zeros could follow. When Japanese fighters tried to escape by diving, Hellcats could follow them down without concern about structural overstress or inability to regain altitude afterward. The engagement lasted approximately 37 minutes from initial contact to the last aerial combat. American pilots claimed 43 Zero kills during the battle. Post-war analysis indicates the actual number was likely 28 confirmed destroyed, plus additional aircraft damaged or forced to crash land. 2 Hellcats were lost during air-to-air combat, 1 to concentrated fire from multiple Zeros, 1 to engine failure possibly caused by battle damage. The kill ratio of approximately 14-1 represented the most lopsided aerial victory in Pacific naval aviation to that date. This was not simply superior pilot skill. Many Japanese pilots at Coeur d'Alene were combat veterans with extensive experience. The difference was aircraft performance. The Hellcat's superiority in speed, climb rate, and structural strength provided American pilots with tactical options Japanese pilots lacked. Bomber losses during the Coeur d'Alene strike were minimal despite the large Japanese fighter presence. 3 SBDs and 1 TBF were shot down, representing less than 5% losses from the bomber force. The Hellcat escort had effectively neutralized Japanese fighter defenses while simultaneously destroying a substantial portion of Coeur d'Alene's air strength. Word of the Coeur d'Alene victory spread rapidly through Pacific Fleet units. The battle demonstrated that American naval aviation had achieved not just parity, but superiority over Japanese fighters. The days of defensive tactics and high loss rates were ending. American carriers now possessed a fighter aircraft that could dominate Japanese opposition. Japanese naval aviation forces first encountered Hellcats in significant numbers during the latter months of 1943. Initial combat reports from squadron commanders noted that American fighters were performing differently than the Wildcats Japanese pilots had faced throughout 1942 and early 1943. The new aircraft designated Grumman Type 6 in Japanese identification systems appeared faster, more powerful, and more aggressive than previous American fighters. Lieutenant Commander Saburo Sasai, one of Japan's most experienced fighter pilots with 64 confirmed victories, provided detailed assessment of Hellcat capabilities based on his encounter with the aircraft in February 1944 near Rabaul. Sakai had extensive experience fighting American aircraft and understood Wildcat capabilities and limitations thoroughly. His encounter with a Hellcat revealed how significantly American fighter performance had improved. Sakai's engagement began when he intercepted what he believed to be a Wildcat conducting reconnaissance over Japanese-held territory. He positioned his Zero at altitude and waited for the American to commit to a specific course planning to execute his standard tactic of diving behind the American during a turn, achieving firing position as the American climbed back to altitude. This approach had succeeded numerous times against Wildcats. However, when Sakai executed the attack, the American aircraft, which he subsequently identified as a Hellcat, performed differently than expected. The Hellcat's acceleration during the initial dive exceeded what Sakai anticipated based on Wildcat performance. When Sakai attempted to follow through his attack run, the Hellcat climbed away faster than Sakai's Zero could pursue. By the time Sakai completed his maneuver and attempted to reposition, the Hellcat had regained altitude and was maneuvering to counterattack. Sakai was forced to disengage. The first time in his combat career, he had been unable to maintain positional advantage against an American single-engine fighter. His after-action report to his squadron commander noted that the new American fighter possessed performance characteristics that rendered traditional Zero tactics less effective. He recommended revised tactical approaches, emphasizing caution and numerical superiority when engaging these aircraft. Other experienced Japanese pilots reported similar findings. The Hellcat was not dramatically superior in all performance categories. The Zero retained advantages in low speed, maneuverability, and range. However, the Hellcat's advantages in the areas that mattered most for combat speed, climb rate, dive performance, and structural strength, were sufficient to fundamentally alter the tactical balance. Japanese intelligence organizations attempted to develop detailed technical information about the Hellcat through analysis of wreckage from downed aircraft. Several crashed Hellcats were recovered from islands and ocean shallows during late 1943 and early 1944. Technical evaluation teams examined engine installations, structural components, and systems. The analysis confirmed what combat reports indicated. The Hellcat was built around a substantially larger engine than the Wildcat, producing approximately 2,000 horsepower compared to the Zero's 1,130 horsepower. The airframe was heavier and stronger, with extensive armor protection and self-sealing fuel tanks. The aircraft was designed to absorb battle damage and protect the pilot, accepting performance penalties from additional weight in exchange for improved survivability. Japanese technical analysts recognized that the Hellcat represented a different design philosophy than Japanese fighters. Zero development had emphasized maximum performance through minimum weight, accepting reduced protection to achieve superior maneuverability and range. The Hellcat prioritized pilot survival and mission completion, accepting somewhat reduced maneuverability in exchange for superior speed, protection, and firepower. This design difference reflected broader strategic contexts. Japan's industrial capacity was limited, and replacing lost pilots was increasingly difficult as the war progressed. Japanese fighters needed to achieve tactical success while minimizing losses. American industrial production could replace lost aircraft rapidly, but trained pilots represented greater investment. American fighter design therefore emphasized keeping pilots alive, even at the cost of additional aircraft weight and manufacturing complexity. By mid-1944, Japanese aviation commanders recognized they faced a serious problem. Their frontline fighter, the Zero, was being consistently outperformed by American Hellcats. Tactical adjustments could mitigate, but not eliminate the performance differential. Some Japanese pilots became more cautious, refusing engagement unless conditions strongly favored them. Other pilots became more aggressive, attempting to compensate for performance deficiencies through aggressive tactics. Neither approach proved consistently successful. Cautious tactics meant yielding initiative to American forces, allowing Hellcats to control engagement timing and protect American bomber strikes effectively. Aggressive tactics resulted in higher Japanese losses, as Hellcat pilots could exploit their performance advantages to defeat aggressive attacks and counterattack effectively. Japanese aircraft development programs attempted to produce improved fighters, but industrial constraints and material shortages delayed introduction of new types. The A7M Repu was designed to match or exceed Hellcat performance, but development problems and manufacturing difficulties meant it never entered operational service in significant numbers. The N1K Shiden possessed performance competitive with the Hellcat, but was produced in relatively small numbers, approximately 1,400 aircraft total compared to over 12,000 Hellcats. The result was that Japanese naval aviation faced American Hellcats with aircraft designed for 1941 combat conditions throughout most of 1944 and 1945. The technological and industrial advantage had shifted decisively to American forces. The decisive demonstration of Hellcat superiority occurred during the Battle of the Philippine Sea on June 19th to 20th, 1944. This engagement, which American pilots subsequently termed the Great Marianas Turkey Shoot, represented the largest carrier battle since Midway and resulted in the effective destruction of Japanese naval aviation as an offensive force. American Task Force 58, commanded by Vice Admiral Mark Mitcher, comprised 15 fleet and light carriers with a total of 956 aircraft, including approximately 480 Hellcats. Japanese Mobile Fleet, commanded by Vice Admiral Jizaburo Ozawa, comprised 9 carriers with 473 aircraft, primarily A6M0s with some newer types. The strategic context was the American invasion of Saipan in the Mariana Islands. Japanese naval leadership recognized that loss of the Marianas would bring the Japanese home islands within range of American B-29 bombers. They committed the mobile fleet to decisive battle, intending to destroy American invasion forces through coordinated carrier airstrikes. Japanese planning relied on several assumed advantages. Japanese aircraft had longer range than American types, allowing them to strike from beyond American counterstrike distance. Japanese land-based aircraft in the Marianas could support carrier strikes, providing numerical superiority. Japanese pilots, while less experienced than the elite groups lost at Midway, still represented better training than American estimates credited. However, Japanese planning did not adequately account for the performance differential between Zeros and Hellcats. American fighter direction systems had also improved substantially since 1942, providing Hellcat pilots with accurate tactical information about incoming Japanese strikes. The battle began on the morning of June 19th when Japanese carriers launched the first of 4 major strikes against Task Force 58. The first raid comprised 69 aircraft, 45 fighters, 16 dive bombers, and 8 torpedo bombers. American radar detected the formation at approximately 150 miles range. Task Force 58 launched every available Hellcat, approximately 220 fighters, to intercept. The interception occurred approximately 60 miles from the American fleet. Hellcats attacked the Japanese formation from multiple directions simultaneously, breaking up the coordinated strike before it could reach the carriers. The performance advantage was immediately evident. Hellcats dove through the Japanese formation at speeds Japanese fighters could not match, destroyed bombers before Zero escorts could intervene, then climbed back to altitude before Zeros could counterattack effectively. The first Japanese raid lost 42 out of 69 aircraft, 61% losses. Only a handful of Japanese aircraft reached attack positions against American carriers, and those achieved no significant hits. The Hellcat interception had been devastatingly effective. Japanese commanders launched subsequent raids, despite the catastrophic losses from the first strike. The second raid comprised 128 aircraft and met similar results. Hellcat interceptions destroyed 98 aircraft, 77% losses. The third raid lost 7 out of 47 aircraft. The fourth raid lost 73 out of 82 aircraft. By the end of June 19th, Japanese carrier air groups had lost approximately 240 aircraft in combat, plus an additional 30 to operational accidents and ditching due to fuel exhaustion. American losses were 29 aircraft, predominantly to anti-aircraft fire rather than Japanese fighters. The kill ratio for fighter versus fighter combat was approximately 13-1 in favor of American forces. The battle demonstrated several critical factors beyond simple aircraft performance. American fighter direction radar and control procedures provided Hellcat pilots with tactical information Japanese forces lacked. This allowed American fighters to intercept Japanese strikes before they reached the fleet and to concentrate force against each raid sequentially. Japanese strikes arrived piecemeal, allowing Americans to defeat each raid with overwhelming local superiority. However, aircraft performance remained fundamental. Even when individual Hellcats engaged multiple Zeros, the performance differential allowed American pilots to control engagement parameters. Hellcats could engage when situations favored them and disengage when threatened, then return to re-engage from better positions. Japanese pilots lacked equivalent tactical flexibility. Their aircraft's performance limitations meant they had to accept engagement on terms American pilots chose. Post-battle analysis by both American and Japanese forces recognized the Battle of the Philippine Sea as decisive. American naval aviation had achieved air superiority so complete that Japanese carrier forces could no longer operate effectively against opposed American carriers. The combination of superior aircraft, superior pilot training, superior tactics, and superior command and control had resulted in one-sided victory that effectively ended Japanese carrier aviation as a strategic threat. Commander David McCampbell, Air Group Commander of Carrier Air Group 15 aboard USS X, became the Navy's highest-scoring fighter ace of World War II flying F6F Hellcats. His combat record demonstrated both the capabilities of the aircraft and the effectiveness of tactics designed to exploit those capabilities. McCampbell graduated from the Naval Academy in 1933 and completed flight training in 1938. By 1944, he commanded CAG-15, comprising 4 squadrons with approximately 70 aircraft. As Air Group Commander, McCampbell was responsible for overall tactical direction, but also continued to fly combat missions, leading strikes and fighter sweeps throughout the carrier's combat deployment. McCampbell achieved Ace Status 5 aerial victories on June 19, 1944, during the Battle of the Philippine Sea, flying as part of the Fighter Director Reserve, positioned above Task Force 58. McCampbell and his division were vectored to intercept Japanese strikes attempting to attack the carriers. During multiple engagements over approximately 6 hours, McCampbell shot down 7 Japanese aircraft, 5 Zeros and 2 dive bombers. His tactics exploited Hellcat performance advantages systematically. He positioned at altitude above approaching Japanese formations, dove through them at high speed, fired during the high-speed pass, then climbed back to altitude before Japanese fighters could respond effectively. This boom and zoom approach had been American doctrine since 1942, but the Hellcat's performance made it far more effective than it had been with Wildcats. McCampbell's most famous engagement occurred on October 24, 1944, during the Battle of Leyte Gulf. He and his wingman, Ensign Roy Rushing, were flying combat air patrol when they encountered a Japanese formation of approximately 60 aircraft bombers with 0 escorts approaching Task Force 38. Despite being outnumbered 30-1, McCampbell and Rushing attacked. The engagement lasted over 90 minutes. McCampbell destroyed 9 aircraft 7 Zeros and 2 Army Type 1 Oscar fighters. Rushing destroyed 6. The 2 Hellcats effectively disrupted the entire Japanese formation, preventing coordinated attack on the American fleet. Other Hellcats from Essex and nearby carriers joined the engagement, ultimately destroying or driving off most of the Japanese force. McCampbell landed aboard USS Langley, having been waved off from Essex due to crowded flight deck with 2 rounds of .50 caliber ammunition remaining and fuel gauges reading empty. He had been airborne so long that deck crews had reported him as missing, and Essex had launched search aircraft to look for him. His gun camera footage from the mission became training material for other fighter pilots, demonstrating effective tactics against numerically superior opponents. McCampbell received the Medal of Honor for his actions on October 24. The citation specifically noted his aggressive tactics, superior airmanship, and effectiveness against overwhelming enemy numbers. However, as McCampbell noted in post-war interviews, the Hellcat's performance was crucial to his success. An aircraft with Wildcat-level performance could not have executed the tactics he employed. The speed, climb rate, and structural strength were essential to attacking, disengaging, repositioning, and attacking again repeatedly over 90 minutes of continuous combat. McCampbell finished the war with 34 confirmed aerial victories, all achieved flying Hellcats. His air group, CAG-15, destroyed over 600 Japanese aircraft during its combat deployment from May through November 1944, the highest score of any Navy air group during the war. The unit's success reflected superior aircraft, superior training, and effective tactics, all integrated into a coherent operational system. Grumman Aircraft Engineering Corporation, as production of F6F Hellcats represented one of the most successful manufacturing programs in aviation history. Between October 1942 and November 1945, Grumman manufactured 12,275 Hellcats at its Bethpage, New York facility, making it the most produced American fighter aircraft of World War II after the Republic P-47 Thunderbolt. Production began slowly, as expected with a new aircraft type. Grumman delivered 12 F6F-3 aircraft in the last quarter of 1942, used primarily for additional testing and initial pilot training. Production ramped up through early 1943, 46 aircraft in January, 51 in February, 76 in March. By April 1943, Grumman was producing approximately 130 Hellcats per month. Peak production occurred in 1944. Grumman produced 6,139 Hellcats that year, an average of 511 aircraft per month. The highest single month was March 1944, when 644 Hellcats were completed, approximately one aircraft every 70 minutes, 24 hours per day. This production rate required 3 8-hour shifts operating 7 days per week, with workforce of approximately 25,000 employees at the Bethpage facility. Manufacturing efficiency improved throughout the production run. Early aircraft required approximately 12,500 man-hours to complete. By mid-1944, manufacturing time had been reduced to approximately 7,800 man-hours per aircraft through improved tooling, better workflow organization, and worker experience. This reduction in manufacturing time, while simultaneously increasing production rate, demonstrated effective industrial engineering. The production program also incorporated continuous improvement based on operational feedback. The basic F6F-3 model was superseded by the F6F-5 variant in April 1944. The -5 model incorporated approximately 500 minor improvements identified through fleet operations, improved engine cowling for better cooling, spring-loaded control tabs for reduced stick forces at high speeds, reinforced windscreen, improved ammunition feed mechanisms, and numerous other refinements. Grumman also produced specialized variants for specific missions. The F6F-3N and F6F-5N were night fighter versions with radar installed in a wing-mounted pod and modified cockpit lighting for night operations. The F6F-3E and F6F-5E were extended-range variants with additional fuselage fuel tanks. The F6F-5P was a photo reconnaissance variant with cameras replacing some armament. Total production included approximately 1,435 night fighters and 200 photo reconnaissance aircraft. Quality control maintained high standards throughout the production run. Grumman's acceptance test procedures required every aircraft to undergo comprehensive ground testing followed by a test flight before delivery to the Navy. Defect rates remained low. Less than 2% of delivered aircraft required return to the factory for correction of manufacturing defects. This reliability reflected both effective manufacturing processes and robust aircraft design that tolerated normal production variations without performance degradation. The financial aspects of the program demonstrated efficient use of military procurement funds. The original contract specified a unit cost of approximately $50,000 per F6F-3, including government-furnished equipment such as engines and instruments. By 1944, manufacturing improvements had reduced costs to approximately $35,000 per aircraft, despite incorporation of improvements that added capability. Total program cost was approximately $450 million, substantial, but representing good value given the aircraft's combat effectiveness. Statistical analysis of F6F combat operations throughout the Pacific War provides quantitative evidence of the aircraft's effectiveness. The Hellcat achieved a combat kill ratio of approximately 19:1 for every Hellcat lost to enemy aircraft. 19 enemy aircraft were destroyed by Hellcats. This remains the highest kill ratio achieved by any American fighter aircraft during World War II. Navy and Marine Corps units flying. Hellcats were credited with 5,223 enemy aircraft destroyed in air-to-air combat between September 1943 and August 1,945. During the same period, 270 Hellcats were lost in aerial combat. The kill ratio varied by time period and theater, but consistently exceeded 10-to-1 even during periods of intense combat against experienced Japanese pilots. The highest kill ratio occurred during 1944, when American forces were conducting offensive operations across the Central Pacific, and Japanese aviation faced acute shortages of experienced pilots. During this period, Hellcats destroyed approximately 3,600 Japanese aircraft, while losing fewer than 150 in air combat, a ratio exceeding 23-to-1. Total Hellcat losses from all causes during the war were approximately 2,462 aircraft. Individual pilot achievements demonstrated the aircraft's capabilities. 306 Navy and Marine Corps pilots achieved ace status, 5 or more victories, flying Hellcats more than any other American fighter type. The top 20 Navy aces of World War II all flew Hellcats for at least portions of their combat tours. 31 pilots achieved 15 or more victories in Hellcats, qualifying as triple aces. The Hellcats' effectiveness was not solely due to aircraft performance. Superior pilot training, effective tactics, and comprehensive command and control systems all contributed to combat success. However, comparative analysis of Wildcat and Hellcat operations under similar conditions demonstrates that aircraft performance was fundamental. Units transitioning from Wildcats to Hellcats showed immediate improvement in kill ratios even before pilots had extensive experience with the new aircraft. Hellcats accounted for approximately 75% of all Navy and Marine Corps' aerial victories in the Pacific theater. This dominance reflected both the aircraft's capabilities and its widespread deployment. By mid-1944, Hellcats equipped virtually all Navy fighter squadrons operating from fleet carriers. The aircraft became the standard against which other fighters were evaluated. Post-war technical evaluations comparing Allied and Axis fighters consistently ranked the Hellcat highly. Navy Technical Mission Japan evaluated captured Japanese fighters against American types in 1945. The assessment concluded that the Hellcat was superior to all Japanese fighters in combat utility, combining good performance with excellent reliability, ease of maintenance, and pilot survivability. The only Japanese fighter judged potentially superior was the S-7M Repu, which never reached operational service in significant numbers. Edward O'Hare did not survive to see the Hellcat achieve the combat success his April 1942 recommendations helped create. On November 26, 1943, O'Hare was killed during a night combat mission, flying one of the aircraft he had helped design, defending the fleet in exactly the role he had trained for. By November 1943, O'Hare had returned to operational flying after the Medal of Honor tour and his Grumman visit. He was assigned to USS Enterprise, CV-6, as commander of the Embark Air Group. Enterprise was operating as part of Task Group 50.2, supporting the invasion of the Gilbert Islands in the Central Pacific. Japanese forces had begun conducting night torpedo bomber attacks against American carrier forces. These attacks, typically launched from island bases, occurred after dark when American fighters had difficulty intercepting without specialized night fighting equipment. The attacks had achieved some success, and Navy leadership was developing countermeasures. O'Hare volunteered to test experimental night fighting tactics using Hellcats in coordination with Raider-equipped TBF Avenger torpedo bombers. The TBF's radar operator would guide the Hellcat to the vicinity of Japanese bombers, whereupon the fighter pilot would acquire the target visually and attack. The tactic was untested but showed promise in training exercises. On the night of November 26th, O'Hare launched as part of a 3-plane Section 2 Hellcats and 1 TB-2 intercept Japanese torpedo bombers approaching. Task Group 50.2. The TBF's radar detected Japanese aircraft, and the formation proceeded to intercept. At approximately 7:45 p.m., the section made radar contact with enemy aircraft approximately 12 miles from the task force. What happened next remains uncertain. The formation engaged multiple Japanese aircraft in darkness. Radio transmissions indicated successful attacks against at least 2 Japanese bombers. However, during the engagement, O'Hare's Hellcat disappeared. His aircraft did not return to Enterprise, and no radio transmissions were received after approximately 7:52 p.m. Search aircraft launched the following morning found no wreckage or debris. O'Hare was declared missing in action, presumed dead. He was 30 years old. The Navy posthumously promoted him to commander and continued the investigation into his loss. The official investigation, completed in 1944, concluded that O'Hare was probably shot down either by defensive fire from a Japanese bomber or possibly by friendly fire from the TBF as tail gunner during the confused nighttime engagement. Definitive determination was impossible without recovering the aircraft or witnessing testimony beyond the limited information available from the surviving crew members who were focused on their own combat actions during the chaotic engagement. O'Hare's loss was significant beyond the personal tragedy. He had been one of the Navy's most visible heroes, a Medal of Honor recipient whose actions at the beginning of the war provided inspiration during a period when American forces were suffering defeats throughout the Pacific. His technical knowledge had directly influenced fighter aircraft development, though this contribution was not widely known outside Navy aviation circles at the time. The irony was that O'Hare died flying the aircraft he had helped design, in combat conditions where that aircraft's capabilities would prove decisive, but before the full extent of the Hellcat's success became apparent. The Great Marianas Turkey Shoot occurred 7 months after his death. David McCampbell's record-setting victories occurred 11 months afterward. The complete vindication of the design decisions O'Hare had influenced came after he was gone. The Hellcat remained in active service with the U.S. Navy until 1954, nearly a decade after World War II ended. Post-war roles included training, reserve squadron operations, and specialized applications that exploited the aircraft's reliability and ease of maintenance. Immediately following VJ Day in August 1945, the Navy began reducing Hellcat inventory as part of overall force demobilization. However, the aircraft's proven reliability and large numbers of trained pilots made it logical to retain Hellcats for training and reserve duties, while newer jet fighters were introduced to frontline squadrons. During the Korean War, 1950 to 1953, Hellcats saw limited combat use. Some F6F drone variants modified as remote-controlled target drones were employed against North Korean targets in 1952. These aircraft were loaded with explosives, flown by radio control toward targets, and detonated. Approximately 30 such missions were flown, with mixed results. The program demonstrated that World War II-era aircraft could be adapted for new roles, though the effectiveness of drone attacks was limited compared to manned strike aircraft. The last Navy squadron to operate Hellcats in primary mission roles was a reserve unit that retired its F6F night fighters in 1954, replacing them with F9F Panther jets. This ended 15 years of Hellcat operations in U.S. military service, though some aircraft remained in storage or secondary roles for several years afterward. Foreign air forces operated Hellcats longer than U.S. forces. The French Navy received approximately 124 Hellcats through military assistance programs between 1950 and 1953. These aircraft operated from the French carrier Arromanches, former HMS Colossus, in Southeast Asia, conducting combat operations during the First Indochina War. French Hellcats flew ground attack missions against Viet Minh forces until 1956, when they were replaced by more modern aircraft. The last French Hellcats were retired in 1961, making the French Navy the last military operator of the type. Uruguay's Air Force received approximately 24 Hellcats in the late 1940s and operated them until 1961. These aircraft served in training and patrol roles, representing one of the longest operational careers for World War II fighters in Latin America. Several Hellcats found their way into civilian hands after military retirement. Some were converted for air racing, modified with reduced weight and enhanced engines for competitive pylon racing events, popular in the 1960s and 1970s. Others became warbird display aircraft, maintained by collectors and museums for historical demonstration. Recognition of the individuals who contributed to the Hellcat's development came gradually, often years or decades after their contributions. Edward O'Hare received immediate recognition through his Medal of Honor, but the connection between his Grumman visit and the Hellcat's design success remained obscure for decades. In 1949, Chicago renamed Orchard Field Airport to O'Hare International Airport in his honor. The airport became one of the busiest in the world, ensuring O'Hare's name remained prominent. However, the airport naming ceremony and associated publicity focused on his February 1942 combat action, not his contribution to fighter aircraft development. In the 1990s, naval historians researching World War II carrier aviation discovered references to O'Hare as April 1942 Grumman visit in Bureau of Aeronautics files. Interviews with surviving Grumman engineers, including Schwendler's assistant, confirmed that O'Hare's combat feedback directly influenced several critical Hellcat design decisions. A 1991 historical study estimated that the design changes resulting from that meeting contributed to saving between 1,000 and 1,500 American pilots' lives through the Hellcat's superior combat performance and survivability compared to the Wildcat. A restored F4F Wildcat, painted in O'Hara's markings, is displayed in Terminal 2 at O'Hare International Airport. The display includes information about his Medal of Honor action and his role in naval aviation during World War II. The display was formally opened on the 75th anniversary of his February 20, 1942, combat mission. William Schwendler received less public recognition despite his central role in Hellcat design. He continued working for Grumman through the end of World War II, leading development of the F7F Tigercat twin-engine fighter and contributing to the F8F Bearcat design. After the war, he worked on early jet aircraft before retiring in 1960. Schwendler's contributions were documented in Grumman internal records, where his name appears as chief design engineer on Hellcat project documentation. However, he never received public recognition comparable to that given to some other aircraft designers. His obituary in the early 1980s mentioned his work on naval aircraft, but did not specifically highlight the Hellcat or the significance of the April 1942 O'Hare meeting. This pattern, combat heroes receiving public recognition while engineers remained largely anonymous, was common in World War II historical narrative. Public understanding focused on dramatic combat actions rather than the technical development work that enabled those actions. Only in recent decades have historians begun systematically documenting the contributions of engineers, designers, and technical personnel whose work fundamentally shaped combat outcomes. The F6F Hellcat's influence on subsequent fighter aircraft development extended beyond its immediate operational success. Several design principles validated by Hellcat combat experience became standard in post-war fighter design. The emphasis on pilot protection, extensive armor, self-sealing fuel tanks, robust structure became accepted doctrine in American military aviation. While the Hellcat accepted performance penalties from additional protection, combat results demonstrated that pilot survival justified these trade-offs. Post-war fighters continued this approach, though improved materials and design techniques reduced the performance impact of protective features. The importance of rapid development incorporating combat feedback was another lesson reinforced by the Hellcat program. The compressed timeline from O'Hare's April 1942 visit to combat-ready aircraft in January 1943, 9 months, demonstrated that focused engineering, effort with clear requirements, could produce effective weapon systems quickly. Post-war development programs attempted to replicate this speed, though institutional and political factors often prevented achieving similar timelines. The value of straightforward, reliable design was validated by Hellcat operational experience. The aircraft's mechanical reliability, low maintenance requirements, few chronic technical problems, high mission-capable rates contributed substantially to its combat effectiveness. Squadrons could generate high sortie rates because aircraft were available and functional. This operational reliability became a priority in subsequent Navy aircraft procurement. The Hellcat also influenced tactical doctrine development. The aircraft's capabilities enabled boom and zoom tactics to work effectively against maneuverable opponents. This validated the approach that became standard in jet fighter tactics during the Cold War: use performance advantages, speed, climb rate, acceleration, to control engagement conditions rather than attempting to outmaneuver opponents. Modern fighter tactics still reflect this principle. 7 airworthy Hellcats remain active today, maintained by private collectors and museums. These aircraft regularly appear at air shows and commemorative events, providing visual connection to World War II aviation history. The number of airworthy Hellcats is relatively small compared to some other World War II fighters, approximately 40. P-51 Mustangs remain airworthy, for example, but sufficient to keep the aircraft's legacy visible to contemporary audiences. The National Naval Aviation Museum in Pensacola, Florida, displays an F6F restored in David McCampbell's markings, showing 34 Japanese victory flags on the fuselage. This aircraft provides visitors with direct visual reference to the most successful American naval fighter of World War II. Similar displays exist at other museums, including the Smithsonian National Air and Space Museum, the USS Intrepid Museum, and various regional aviation museums. The historical lesson from the Hellcat story extends beyond technical details. The aircraft succeeded because combat experience directly informed design decisions, engineers implemented changes effectively, and commanders trusted both groups sufficiently to authorize rapid modification of development programs based on limited but high-quality data. This integration of combat feedback, engineering capability, and institutional flexibility represents a model for effective weapons system development that remains relevant decades later.